First, let's look at the Forest law, which is the heat transfer rate, okay, equals to negative Ka times partial dt over partial dx. As we said, if it's a steady state case, and in this schematic, the temperature distribution is a straight line across the wall, okay? And the temperature gradient is T1 minus T0 divided by X1 minus X0, okay? So if we rearrange the variables, we put this on the leaf, okay? Then it becomes Qx equal to T0 minus T1 divided by L over Ka. Okay, the reason that T1 and T0 switch and is because we have a negative sign here. We get rid of the negative sign and then we switch these two numbers, okay? So that's why it becomes T0 minus T1. Okay, we know that T0 minus T1 is the temperature difference. And in the introduction module, we said temperature difference is the driving force of the heat transfer. Okay, so this is the driving force. And the Qx is the flow rate, let's say flow rate of heat, right? So if we know that, okay, there's a flow rate of something and there's a driving force and divided by a quantity, this is normally can be viewed as a resistance to the flow of something. So to help us to understand this, let's look at the electrical circuit, which is shown by this image. Okay, this is the simplest electrical circuit, right? You apply a voltage under the two ends of the resistor. So U0 and U1. So the driving force for the current is the voltage, which is the U0 minus U1. And you have the current passing through this resistor. Current is basically the flow rate of the charges passing through the region, okay? So this is also the flow rate, let's say, of something, right? And it is charge of the charges. Okay, right? So this is the driving force. And this is the electrical resistance, right? So this is the resistance which resists the charges passing through this resistor, okay? So these two cases are analogous. Now, let's put them side by side to make a comparison. So for electrical circuit, you have the driving force, which is the voltage difference. And for heat transfer, you have the driving force, which is the temperature difference. For the flow or the flow rate of something, for charge is current. For heat is heat transfer rate, okay? So for the resistance, electrical resistance, which is R, and also for this quantity, which is here in this equation, is defined as thermal resistance, okay? That's why L over Ka is called thermal resistance, okay? This is actually a very important concept. You needed to know this. And the unit is W is watts over K, right? Because if you look at the unit, it's meter divided by watts, meter K times meter squared, right? So you get rid of the meters and the K goes to up. That seems this is not correct here. Okay, should be K over W then. Okay, I needed to fix this. Anyway, so L over Ka is thermal resistance. However, there's one constraint. Current in an electrical circuit is always a constant. No matter where you measure the current, like here or within the resistor or here, it doesn't really matter, it's a constant. So in order to apply this analogy, you need to have a constant heat transfer rate, okay? So Qx must be constant over the length or the thickness of the plate, okay? So that's one constraint. And also watch the terminology. Now we know thermal conductivity, receptacle of the thermal conductivity is called the thermal resistivity. L over Ka is called the thermal resistance. Ka over L is called the thermal conductance. So sometimes we get confused by the names. However, K, thermal conductivity, and L over Ka, thermal resistance, is the most are the most used ones. Okay. Okay, so the real world examples or applications. So in Canada, in the housing construction industry, because Canada is very cold, right? And in the winter, you wanted to prevent the heat loss through your wall. So that's why there's a code that requires you to insulate your wall. So you needed to insulate by, maybe there are two major methods. One is you buy fiberglass insulations, which is a pack like this. It's a pack of fiberglass. And the key parameter is called R value, right? Which they show on their package, right? And the R value tells you what is the thermal resistance. And R value equal to the thermal resistance times the area, okay, which is L over K. Now becomes, you can understand the R value is, because it's times the area is 1 meter square if it's 1 unit area, right? So it's basically if you have 1 meter squared, say this is 1 meter wide, 1 meter long. So what is the thermal resistance provided by a 1 meter squared area of this material, okay? So by looking at the R value, you will know what is the thermal resistance provided by this material. So now you know, okay, if the R value is high, then you have a higher thermal resistance, then you can limit the heat loss through the wall, okay? So your house will have a better energy efficiency. Okay, now how to use the analogy to solve the heat transfer problems. When the analogy to electrical circuit can be applied, if the heat transfer rate is a constant, again, the equivalent thermal circuit method will provide a simple and effective way for conduction analysis. Okay, now let's look at the example. Now we stack 3 layers of different materials together. Material A, B, and C, okay? And then you know what is the temperature at the inside, let's say one side, and what's the temperature on the other side, T0 and T3 are known. And then you wanted to know what is the temperature distribution, right? Because now you got 3 materials, you got 3 different thermal conductivities, and also these 3 materials have different thicknesses like LA, LB, and LC. If you just use the partial differential equation, which is the heat diffusion equation, I mean, solve these equations like it's much more difficult. However, if you apply the analogy to electrical circuit, that becomes much easier. Okay, now first of all, we know that each layer gonna have a thermal resistance, right? So you got a thermal resistance, like say RTA, and you got a thermal resistance for material B, which is RTB, and also you got a thermal resistance for C, RTC. And in this way, because they are stacked together, it's connected in a serial connection method, right? So comparing to the electrical circuit, it's basically you serially connect 3 resistors together, which is RA, RB, and RC here. Now, to calculate the heat transfer rate, in this case, that's what you wanted to know, right? First, before you calculate the temperature distribution, you needed to know what is the heat transfer rate first. In the electric circuit, you needed to calculate what is the current, which is I. For this case, if you know U0, U3, and you know what is RA, RB, and RC, it's so straightforward to calculate what is the current, which is U0 minus U3 divided by our total. Our total is RA plus RB plus RC, right? This is our total. Okay. In the heat transfer case, it's the same. So now, for the heat transfer rate equals the overall temperature difference, which is T0 minus T3 divided by our total. And our total, the way to calculate our total, thermal total, is the same as the electrical circuit. So our thermal total equals our thermal A. So thermal resistance A, thermal resistance B, thermal resistance C. You just sum them up, okay? So you will be able to calculate out what is the heat transfer rate in this case. Now, if you know what is the heat transfer rate, then you will be able to calculate what is T1 and T2 in this case. Because if you go back to the electrical circuit, if you know what is the I, it's so easy to calculate what is U1 and U2 because I is constant anywhere. So, which means U0 minus U1 divided by RA, I equal this equation also valid, right? So if you already know I, you know U0, you know RA, you will be able to calculate U1. Same for R2, right? It's U1 minus U2 divided by RB equal to I, okay? You already calculate out what is U1, then you will be able to calculate out what is U2. Same for the heat transfer case, right? You already know what is Qx. You already calculate out here. And then T0 minus T1 divided by RTA should equal to the heat transfer rate. So now it becomes T0 minus T1 should equal to Qx times RTA, right? So T1 then becomes T0 minus Qx times RTA, right? So, sorry, T1. So now you know T1. Again, using this equation, you will be calculating out T2 must be T1 minus Qx RTB, okay? So now you get T1 and T2. And we know that because Qx is a constant, which means in this case, there's no thermal generation, which means it's a steady state case, right? Must be, because otherwise, if your Qx is not a constant across this wall, then which means that your Qx in is not equal to Qx out. In that case, we will have temperature difference because you have the change of the stored energy within this element, which means temperature will change with time, okay? Okay, so this case is a steady state case. If you know T0, T1, T2, and 3, you just need to use a straight line to connect them together, right? And then you know, okay, how the temperature is distributed across the whole wall, which has 3 layers of different materials, okay? So that's the analogy to electrical circuit, and we can see like how simplified, okay, for the calculation process if we use this analogy. All right. The analogy can be also applied to the convection as well. Okay. So if you look at the Newton's law of cooling, all right, for this case, you have a solid here, you have convection on top of that. And in this case, it seems like the T fluid is a cooling case. Okay, so it's smaller than T solid. So heat transfer is going to the fluid. Now it becomes Ts minus T influid or T fluid. Okay, now heat flux is this equation, heat transfer rate. Be careful, okay? When we apply this analogy, we are talking about heat transfer rate, not the flux, okay? Not the flux. So heat transfer rate, Qy, equals HA times Ts minus T infinite. So if we put this underneath, it becomes this form. All right. Again, here, this is the driving force. This is the flow rate of heat. Then this becomes the resistance. Okay. That's why for convection, the thermal resistance is defined by 1 over HA, which is the heat transfer coefficient times the area. Okay. So recall, this is for conduction, L over Ka. This is for convection, 1 over HA. Okay. You need to memorize these two expressions. Okay. Now, previously, we talked about case, which you have only conduction and you have a fixed temperature on the two sides. Now we can make the case more complicated. So if you think about, you have a wall, which has 3 layers, and then you have convections on the two sides of the wall, okay? You got a hot fluid flowing on the left side and the cold fluid on the other side, okay? So in this case, again, you have heat transfer across the, the convection layer, let's say. So you have thermal resistance here, okay? So you have thermal resistance for convection on the other side of the wall. You have thermal resistance for conduction within the 3 layers, okay? So this is convection, this is conduction, 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 and here is convection. And each one got a thermal resistance, right? And we know that for, go back to this, we know the thermal resistance for convection and for conduction. So we just needed to put them together, okay? So again, this is connected in a serial method, which means the total thermal resistance is the summation of each thermal resistance. For the inside, left side, let's say, for convection, it's 1 over H. Here, HA means hot fluid. So hot fluid times the area. This is the conduction thermal resistance for layer A, layer B, and layer C. Again, for the outside, for the cold fluid, we also have the convection thermal resistance. So the total is the summation of all of these terms. Once you got the total thermal resistance, then calculating the heat transfer rate is so easy, right? It's equal to the overall temperature difference, which is the driving force, T0 minus T5, okay? So T0 minus T5 divided by the total thermal resistance. Once you have the Qx, again, you will be calculate out what is T1, T2, and T3, and T4 using the same method as we demonstrated previously for the conduction case, okay? And then once you got all of these temperatures, you will know what is the temperature distribution, okay, within the wall. Within the Within the convection layer, that's going to be more difficult to know the exact profile, but normally it will be profile like this, okay? So you have a layer that is affected by the heat transfer, which is called boundary layer, but we're going to talk about this in the next module. For now, you just need to know, okay, the profile is roughly like this. However, within the solid, you must know, okay, it's a straight line. You know exactly what they are, okay? So that's the analogy to the electrical circuit for both conduction and convection.